Okay, welcome to lecture. And again, we'll get started here, chapter 15, I think, still. And again, like you're doing there, put here there for attendance in the chat. We let everybody in. And again, we're going to pick up where we left off last time. All right, so looking like everybody's coming in. So again, if you're just coming in, make sure you put here in the chat there for roll. And we're going to pick up again, lecturing where we left off. It should be right around here, I believe. Okay, so last time we finished lecturing on buffers, and we talked about obviously how to make buffers, how buffers work. We talked about calculations with buffers. So remember that buffers are essentially solutions that contain either a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. Again, they do have to be weak acid or weak base in order for those guys really to set up the equilibrium. And when they do, what that means is in that solution to begin with, as we talked about, you have pretty much like an acid part and you have a base part to that buffer to begin with. And that is why buffers can resist changes in pH, even when you add acid or base to them, because they do have an acid part and they do have a base part. And as we talked about, essentially what will happen is if you add an acid to the buffer, the base part of the buffer will react with it. It will also produce some more of the acid part of the buffer. But more importantly, as we saw and we talked about, it will not allow free H plus to be produced from the addition of that acid. And by keeping the H plus concentration relatively constant, it will also keep the pH relatively constant. Same thing happens if you have a buffer and you add a base to it. The base will react with the acid part of the buffer. And really what's preventing happening in that case is when you add the, say, sodium hydroxide or a base to it, for example, it will prevent the production of OH minus from being made, so free OH minus. And that's really important because free OH minus or OH minus concentration is tied to the H plus concentration. So the same sort of effect occurs if we're able to keep our OH minus concentration level. What that means is our H plus concentration will also remain relatively level and the pH should remain relatively constant as well. Remember that those things work opposite of each other. So as one goes up, the other goes down. And as the H plus goes up, the OH minus goes down and vice versa. So really that's how a buffer works. They basically prevent the formation of free H plus if you add acid to it, or prevent the formation of free OH minus if you add base to it, both of which ultimately keeps the H plus concentration relatively constant and also keeps the pH relatively constant. So as we talked about in reality, though, if you do add acid or base to a buffer, you will see the pH move if you're monitoring it. But what we're talking about and sort of not having it change very much is that we're not seeing ginormous sort of jumps in pH. So for again, an example, if your pH started at a pH of 6 and you added acid, you wouldn't see the pH go from 6 down to 2 or 1 or, anything like that. Perhaps it drops down a little bit, 5 point something, 5.9, something in that ballpark, 5.8. But we do see a slight decrease in it, but not a tremendous jump in the pH as we would expect in a non-buffer situation. Remember that buffers are really common ions problems because they do contain basically like a weak acid and its conjugate base or a weak base and its conjugate acid. And that means that in terms of calculations, we can use an ice table like we've been doing. Or we could use the Henderson Hasselbalch equation, which is the pH equals the pKa plus the log of the base over the acid, whereas we did a number of examples last time, the pKa is minus the log of the Ka value. And we can use that Henderson-Hasselbalch equation in place of a ice table, or as we saw, you could also use an ice table if you choose to do so. Again, important if you do the ice table approach rather than the Henderson-Hasselbalch, that you make sure that you have an initial amount on the product side for either your conjugate acid or conjugate base, depending on the buffer that you're doing. In addition, if we add some volume to a buffer, so if we have a certain amount of buffer and then we decide to add something to it, like some acid or base to it, we do have to do an ice table, and the ice table does need to be done in moles. Again, whenever you're adding any type of volume, you need to do the ice table in moles. Once you do that initial ice table, you can convert back to molarity using the total volume like we did in some of those examples. And remember that once you do that, you will still have a buffer left over in most cases. And at that point, you do have two options. After you do that first ice table, you could either do, again, a second ice table with molarity and solve for X, or you could, again, go into the Henderson-Hasselbalch because it is still a buffer at that point. Any questions on any of that stuff we talked about? Again, the other important thing, again, is that a buffer is not necessarily a neutral solution. You can have a buffer that is made at any pH you like, between like 0 and 14. Again, what the definition of a buffer is just that it basically can maintain its pH even if you add acid or base to it. Any questions on any of that buffer stuff that we talked about? Okay, so this is, I think, where we left off, and we're going to get into sort of the next sort of challenging thing for people, and that is titrations. And let's talk just a little bit about titrations in general. And I'm assuming if you're in this class, you probably have done a titration somewhere along the way. Usually, like in the first semester, they make it a big experiment and stuff to do, some type of titration where you try to find the unknown, maybe a concentration or something like that. So in a titration, we usually add a solution of known concentration sort of gradually to a solution of unknown concentration. And again, based on stoichiometry, based on volumes and stuff like that, you typically can figure out things like the concentration of an unknown. You can even find things like molar mass of the unknown, equivalent mass. You know, there's a lot of things you can kind of do with a titration. Typically what we use for titration is what we see here. We typically have down here a flask, right? Inside the flask, a lot of times is the acid, doesn't always have to be the acid down there. So for example, we can put our sodium hydroxide up here, and that's a burette, right? And you open the burette and it drops, in this case, if we were doing this acid-base titration, it would drop the sodium hydroxide into our acid. We would also usually include something like an indicator, which is like this bottle here. And a very common indicator that a lot of people use, especially for acid-base titration, and you probably did as well, is one that's known as phenolphthalein. Phenolphthalein is a indicator. We're going to talk about indicators towards the end here of this chapter, but indicators essentially work basically off the principle of pH ranges. So they basically will change color within a specific pH range. So for example, something like phenolphthalein is actually colorless in acidic solution. It's actually colorless in neutral solution, but it does turn kind of that classic pink that a lot of people are used to in a basic solution. So for example, phenolphthalein, off the top of my head, runs off of a pH range of like 8.3 to 10-ish in that ballpark in terms of pH. So around 8.3, it's pretty much colorless, so just a hint of pink. Obviously, you get closer to that 10 range, it becomes dark, dark, super dark pink. And usually when we do this type of titration, we continue to add, for example, in this example here, sodium hydroxide to the acid, and we continue to add it until it reaches what is sometimes referred to as the equivalence point. And typically the equivalence point in an acid-base titration is usually that point where the moles of acid equals the moles of the base. So that's typically the exact spot where your moles of acid and your moles of base basically will equal each other. And that's sort of usually your definition of an equivalence point. Not to be confused with was sometimes referred to as the end point of a titration. The end point of a titration is sort of where you lay up the titration and sort of stop doing your titration. Now, obviously, if you do a good titration, your end point should be very close to your equivalence point, right? Because that's usually the goal of most titrations that you do, is to get to that equivalence point. Again, like I said, typically we use an indicator to tell us, hey, perhaps we should stop. And again, you can see here, this is, I think, phenolphthalein, and you can see that very kind of light pink color when it changes. And we're going to talk about a couple of things in titrations that you commonly will see, but usually you will be told that you want in that type of titration to stop when it's like the lightest, super lightest shade of pink that you could see. Like you just put a white piece of paper up underneath it to kind of see the pink color. That obviously stays. And that's because, again, phenolphthalein works over a pH range. And usually when you use that indicator, you're using it for a solution or a reaction that changes pH right around 8.3, which technically is still kind of colorless for phenolphthalein. But as soon as you can kind of visually see that lightish color of pink, that will tell you you're probably near the equivalence point. We'll also talk in here, and we'll see as we go through some of these calculations and answer a very common question or a very common thing that you hear when people do titrations, especially if you've had experience in this as well. You might have heard people when they do the titrations, I don't understand it. I just added one more drop and the thing went from like no color to super dark pink. And we're going to explain why that happens as well. And that's usually a very, very common thing that you hear when people do titrations, like, oh, I can't believe it. I just added one drop. It went like super dark. I should just throw it away and start again. We'll also see why maybe you don't need to throw it away and start again. It's probably okay as we look through these calculations. Obviously, not all titrations are acid-base titrations, but obviously in this chapter, that is what we're mainly focusing in on, obviously, is acid-base titrations. And again, you can do sort of slightly different titrations. You can even do titrations where you make a solid and precipitate out some stuff, but usually acid-base titrations is usually what people are sort of referring to. So let's talk about some different types of titrations. And this is the very first type of titration we're going to talk about here. And this is a strong acid and a strong base titration. So for example, if we take something like HCl, which is hydrochloric acid, and we react it with sodium hydroxide, which is a strong base, we're going to get some water. And we'll get a little sodium chloride action going on. And this is the overall reaction. Just so everybody's clear, we are at this point, just so you know, up in the burette is our sodium hydroxide. So we're adding the sodium hydroxide to our beaker, to our flask. In this case, the HCl is down in the beaker or the flask. Obviously, an indicator would be added in this particular case. So one important aspect of calculations that involve titrations is that idea that we talked about when we got into buffers. And that was the idea that when we do add volume, we are changing the molarity. And there is no other place where you are constantly pretty much adding volume every second of the way, which it happens in a titration, right? So in a titration, you are constantly adding volume. And what that means is when you do these calculations, it will require some ice tables to be done. And just like with the buffers, when we add something to the buffer, we do have to do those ice tables in terms of moles. So again, in that first ice table, you do want to use moles when you do these calculations. And again, just like before, especially in titrations, after you do that very first ice table that you might have to do, it is very good practice to convert it back to molarity. So again, you would use the total volume to do that. That's how much you started with, say, in the flask or the beaker, and how much, say, sodium hydroxide in this example that you added to it. So What we see on the screen was referred to as a titration curve. And our titration curve here typically will have the pH on the Y. On the X, in this case, we're adding sodium hydroxide. So that's the total volume of sodium hydroxide that we're adding. So we're going to talk about some of these different parts along this curve, but this is a typical titration curve, sometimes referred to as like an S curve, as you can kind of see. It kind of makes like an S. And we're going to talk about each of the parts of this titration curve and how to kind of go about the calculations when you're here. And at this point, what we're talking about is specific to this type of titration, which is a strong acid and strong base titration. So let us start with right here at volume 0. Before we add any sodium hydroxide to this reaction. So I'm just going to flip the page here to on the right. So before we add base, if you think about what you got going on in your beaker is, in this case, you just have HCl. So at this point, before you start the actual titration, before you start adding anything from the burette down into your beaker or your flask, the only thing that you basically have in there is a strong acid like HCl. And obviously, we should know hopefully how to calculate the pH of a strong acid. At this point, you would just have to go right into the pH equation. pH equals minus the log of the H plus. At this point, because you have not added any base to it, there's no need to convert things to moles, no need to figure out a new molarity or anything like that. It is simply just the solution out of the bottle with its own molarity. So in this type of titration, before you actually started, if you wanted the pH of the solution, it's very simple to figure out. You pretty much could go right into that pH expression. Again, remembering that something like hydrochloric acid, when it breaks apart, is 100% going to break apart into ions. And again, in this particular case, it's a 1-to-1 relationship between the HCl and the H plus, which means if you knew the concentration of the HCl, you just take minus the log of it, and you're good to go there on the initial pH of your solution before you start it. Any questions on the initial part of it? So let's take a look at our graph here. We decide, all right, we probably should add perhaps some base to it. So we'll go here with red. So once we start adding some base all the way up to the equivalence point, we are definitely adding sodium hydroxide in this case, which means that we are adding volume, and we do need to do an ice table. And the purpose of this ice table is to figure out what's left over after we add the sodium hydroxide. So let's take a look at sort of what that might look like. So when we start adding base, up until before the equivalence point, we're going to need to do an ice table. So I'm going to take my reaction that we had, HCl plus some sodium hydroxide, sodium chloride, and some water. Okay. Now, just to be clear here, I'm going to be making up these numbers here. All right. So I'm just making up these numbers. I didn't find them anywhere. I'm just literally making up the numbers right now. So what I'm going to say is, in my beaker that I'm titrating, I'm going to say I started with 4 moles of HCl. And again, I just randomly picked that number. Obviously, it does need to be in moles because we're adding, right, sodium hydroxide to the HCl. So if it wasn't in moles, you most likely will have the volume, right, and the molarity, which, as we've done a number of times up to this point, you should be able to figure out how to get the moles. Now, if I am actually before the equivalence point, you need to think about, should the number of moles of my sodium hydroxide, so this is basically what I'm starting with, right? And this is what I'm adding, right? should the moles of my sodium hydroxide be less than, equal to, or more than the moles I started with? So remember, though, that when you reach the equivalence point, what that means is the moles of the acid equals the moles of the base, which means if I have not hit the equivalence point, that means that the moles of sodium hydroxide I am adding should be less than what I started with. So again, here, I'm just going to make up a number. I'm going to go with 2 moles of sodium hydroxide. Again, just made it up. I'm going to go with 0 this guy on this side. Now, because this is a titration, and because we have not reached the equivalence point in this case, we could think about what would get used up. And you could just make it based on logic and also the idea of sort of limiting reagent, excess reagent. In the comparison of these two numbers, I have way less sodium hydroxide. It's all one-to-one relationship. So I have a way less sodium hydroxide, which means I have not reached the equivalence point. And that should be what will be used up. So the change here will be minus 2 moles, minus 2 moles, plus 2 moles, which means at equilibrium, I would have 2 moles of this guy, nothing of this guy, and 2 moles of this guy. So this is kind of what your first ice table would look like. It would be done with moles. Again, after you are done with the first ice table, you should convert this back to molarity. So we need to divide by the volume to convert these guys back to molarity. The volume here would be the total volume. And that's going to be the volume of, say, the acid plus the volume of the base added. Now, people sometimes get confused when they're doing titrations as to, all right, what do I do now? And you can use your ice table to help you sort of logically think about what you got going on there. So when we look at this, what we have left is sodium chloride, and we have HCl. Now, some people may be tempted to go, well, that's a buffer, right? I got 2 numbers. But you hopefully should know that that is not a buffer, because a buffer cannot be made of a strong acid. So that is definitely not a buffer. But the couple of things that we do see here is we do see sodium chloride. And if you remember our talk of salts, sodium came from most likely sodium hydroxide, as you can see. The chloride came from HCl, both of which means that sodium chloride is a neutral salt, which means it is not going to affect the pH, so you don't have to worry about that. So ultimately what you have here at the end of this first ice table is you basically still have the strong acid, which is going to be the major contributor to the pH. And because it is still a strong acid, you can automatically go into pH equals minus the log of the H plus. So you can see that this calculation here is a little bit different than the beginning one. Once you actually start the titration all the way up until you reach the equivalence point, you have to do at least 1 ice table. The real purpose of that ice table is to figure out what is your new concentration of strong acid. And once you get your new concentration of strong acid, you can go into the pH equation and get your pH in that case. Any questions on that? So let's take a look at our curve, and we see a couple of things. So all the way through here where I circled, again, is going to require 1 ice table done in moles. Once you're done with that first ice table, convert to molarity, and then go into the pH equation to get the pH. Now, what we see is as we approach the equivalence point there, we are going pretty vertical. And that's typically what you see is as you approach the equivalence point, you typically see a jump to the equivalence point. And as you can see, after the equivalence point, you usually see a sort of a jump in pH as well. So you usually kind of see that jump to the equivalence point, and then you usually see that jump after the equivalence point. But what we see is as we come towards the equivalence point, which I'll just circle right here in green, at the equivalence point, we see this vertical rise. And this is what answers the common thing that people say when they do a titration of, I just added 1 drop and the color went super pink. And the reason that occurs is you could actually see it here on the graph. As you reach the equivalence point, let's try to draw a box this way. You are going pretty much vertical, which means on this graph, if you're going vertical, you are changing the pH a lot, but the volume itself is not changing a lot. So what that means is as you reach the equivalence point, you need a little bit of volume to change the pH a lot. So why does that make your solution go like super pink? It's because your indicator works over a pH range. So even though in your eyes you added 1 drop, that was enough to make the pH go from like a pH of 8.3-ish, maybe in that case, to maybe a pH of 9, 10, even though you added just 1 drop. And what you're going to visually see in that case is your solution will go from kind of colorless to now your solution is like in the 9-ish, 10-ish range in terms of pH, and you're going to get that dark, dark pink color that you see, even though you're like, I just added 1 drop. And that is also why if you're doing sort of just a regular titration, even though they beat in your head, light color pink, in reality, if you really just miss the equivalence point by a couple of drops here, and even if you saw the thing go like super pink, the reality of it is if you were going to pull the equivalence point volume, even if you missed it by a drop or two, it's all going to end up pretty close to each other, which means in reality, if you ever did a titration earlier on in your life and you only added a drop or two and it went super pink and you were worried about it and they made you like redo it, you really didn't need to probably. You were probably okay. Now, don't get me wrong. If you sat there and just opened the thing up and overshot it by more than a few drops, you probably should redo it. But again, if you miss the equivalence point visually by a drop or two or a few drops, in the end result of your calculation probably would not have made a tremendous amount of difference. Although sometimes first semester instructors like to make you redo it until you get that lightest color pink. But again, as long as you didn't miss it by putting a ton in at that point, your calculation probably would have been okay. And that's why sometimes what people will tell you is it's kind of maybe more important in that situation where you're doing sort of a regular titration that the volumes that you get to reach the equivalence point are very close to each other in terms of how much volume you need to get to that equivalence point. Sometimes a little bit more important, than the visual aspect of it in terms of color, whether it's super light pink or dark pink. Any questions on that? So then let's talk about what happens when we actually do hit the equivalence point. Obviously, as you can see, we're starting to rise in our pH, right? And that also makes sense because we're adding sodium hydroxide. So our pH should start to go up. And obviously, we're seeing this big kind of jump to the equivalence point. So let's go through sort of what happens at the equivalence point. So again, I'm just going to use sort of my made up numbers. So if we are at the equivalence point, and we take our reaction, our HCl plus our sodium hydroxide, gives us some H2O, a little sodium chloride. And again, we're going to continue to do this in moles because we're continuously adding volume. So if we start with, again, my made up number of 4 moles of HCl. Now, if I know I am at the equivalence point, I already know that the definition of equivalence point is the point where the moles of acid will equal the moles of the base. So I should know that the moles of sodium hydroxide, so again, I'm starting with this guy in my beaker or flask. I'm adding this guy. So what that means is if I am at the equivalence point, what I am adding should be the same number of moles of what I started with. So this number in this case, I know should be 4 moles. And again, we will have 0 over here. Now, when we get to the change part of our ice table, you really can't screw it up, I guess is a good way of saying that. There's only one number to choose, so the number's got to be 4 in my example. So we got to get rid of the 4, got to get rid of the 4, we got to add the 4 over here. Which means at equilibrium, we'll have nothing of that guy, which is essentially what the equivalence point means. We will have 4 moles of our sodium chloride. We will divide it by the total volume. And again, that will give us molarity. So ice tables are really important, especially in titrations, because again, sometimes people are like, not really sure where to go from here. So a lot of information can be found in the actual ice table. We could see that absolutely the only thing we got going on at this point is this salt, right? And we've already talked about this salt in the previous problem, but this salt again comes from group 1, which is our sodium ion, and Cl-, which comes from hydrochloric acid, which again means this is a neutral salt, which means the pH should be 7. So really, if you see that you are doing a titration of a strong acid with a strong base, you don't actually have to do any calculation, because no matter what combination you put together of a strong acid and a strong base, when you get to the equivalence point, the only 2 things that you'll have there is water, which is technically neutral, and you will have a salt that basically comes from a strong acid and a strong base, which means that the salt itself is also neutral. So truthfully, you don't have to do any calculations in this type of titration. And if we look at our graph, we see that at the equivalence point, right there is our pH of 7. So it does become 7 at the equivalence point. So the good news, if you're doing a strong acid, strong base titration, you're at the equivalence point. Pretty safe bet. Write a pH of 7 and sort of move on to probably the next part of the question, because it should always end up that way, no matter what combination you did. So the question is, how do we know in this ice table that we were at equal amounts of moles? So we know for sure that the definition of equivalence point is equal numbers of moles. And that's why they're both 4. And again, that's different than what we saw here in the previous ice table. In the previous ice table, we know that we are before the equivalence point, because what we are adding, which is the sodium hydroxide here, if we were at the equivalence point in this example, it should be 4, like it is in the next table. But because it's not 4 and it's less than 4, what we know is we are before the equivalence point. So when you are before the equivalence point, whatever you're adding, which in this case is a strong base, so whatever you're adding, you should have less moles than what you started with. So really, before the equivalence point, what you are adding is kind of like the limiting reagent. You don't have enough, so it's basically the limiting reagent before the equivalence point, and that's always usually going to be whatever you're adding. Other questions I can help you with there? Okay. So then let's talk about what happens now that, we put the indicator in, that thing turns pink, but it's just a recommendation really, right? Why stop when it turns pink? That's no fun. So let's just say, you missed the big pink solution turning, or let's just say you forgot to put the indicator in, which is very common as well. People forget to do that. And you just continue to go past the equivalence point. So as I mentioned before, when you get past the equivalence point, we'll kind of make that purplish. When you go past the equivalence point, again, you typically will see that rise in pH, and eventually it will level off, which is what we kind of see at the top part of the curve there. Eventually it will kind of level off, which gives you that sort of complete S look, right, as it comes down. And what we happens after the equivalence point is important too. So let's talk about sort of a calculation of what that would look like. So at this point, we go in after the equivalence point. Again, that indicator really didn't stop us. So let's talk about what happens at this point. So if we have HCl and we have some sodium hydroxide, got a little sodium chloride and some water. And again, here, we're going to do an ice table. And just to kind of keep it consistent, I'm going to start with my 4 moles like I did in all the previous examples. And again, just making it up. And a reminder, again, this is what we're starting with. And this is what we're adding. And if we know we are past the equivalence point, that means that, remember that the equivalence point is equal amounts of acid and base, which means that if we get past the equivalence point, whatever we're adding is more than what we started with. So again, that's basically practical aspect. You're sitting on the burette, you open it up, you just let it drain in there. Maybe you've done it as well when you're cleaning up, right? At the end of your titration, you open it up, you let all like the base drain in there, see how dark of a pink color you could get in your solution. Maybe you've done that before. So what that means is, again, making up this number, I know that I need to have more moles of what I'm adding than what I started with. So I'm just going to use 6 moles in this case. And again, 0 of this. And what we can see from the table, and the table helps us if you're not sure what you should do, is we actually see at this point, there's kind of a switch that occurs between these two guys. At this point, because we just blew past the equivalence point, we now have added more moles of our sodium hydroxide in this example than moles of our acid we started with. And what that means is our HCl will now become like our limiting reagent, which means the change part in this case is actually going to be the acid. So it's going to be 4 moles minus 4 moles and plus 4 moles. And that means 0 for this guy, 2 moles, and 4 moles. I'm not sure why I capitalize that L, but we'll go with it. And again, logic also tells us that if we took minus 6 here, we would get a minus 2, which you can't have a negative concentration, right? So it's always got to be the smaller number when you're doing the ice table in terms of subtracting. In most cases, I won't say 100% of the time, but probably 99% of the time. Now, just like normal, we want to do the right thing. So we want to take the total volume and we want to convert it back to molarity. Again, we're going to use the volume of acid we started with and the volume of base that we added to it. So again, you could go to your ice table and try to figure out what's going on. So at this point, we do have sodium hydroxide left. We do have sodium chloride left. So clearly, again, here we have 2 numbers. So we just want to put it into the Henderson Hasselbalch equation. And you don't want to do that because that's going to give you an X. Because A, that is not a buffer. Those 2 things are not related to each other. And again, this is where people go bad a lot in titration problems. They end up their ice table with like a couple of numbers and decide, I'm just going to put everything into the Henderson-Hasselbalch equation. So let's take a look at what we really have left over. We've talked about a number of times at this point that this guy here is a neutral salt, which means we don't really have to worry about it or its number that came along with it. What we have here is a strong base, which does make sense if you think about what you're doing at this point. You went right past the equivalence point, you opened it up, you just kept going. You're essentially just dropping strong base into your beaker or flask at this point, which means because this is a strong base, you can get the OH minus concentration from it, which means you could then calculate the POH. And from that, by subtracting 14, you could get yourself to the pH. So when we go past the equivalence point in this type of titration, it does require 1 ice table. The purpose of that ice table is to figure out how much strong base you have left over. And once you figure out how much strong base you have left over, that will get you to, like I said, the OH minus concentration. That will get you to the POH, and you can subtract 14 and get to the pH. Any questions on that there? So in this simply looking sort of titration curve, there's actually 4 distinct sort of problems that you deal with. And that's why it's extremely important. That's why it's extremely important to make sure that you actually know where you are in the titration, because if you kind of know where you are in the titration, you will kind of know what type of problem you should be doing. To answer your question about why is the change -4 in this case, the change is -4 in this case because if we just look at the original numbers we had before we got to the change part, we had 4 moles of HCl, and we are past the equivalence point. So in my example, we had 6 moles of sodium hydroxide. And what that means is you can keep it really simple thinking in terms of like limiting and excess. You could look at those numbers and know, well, I got an excess amount of sodium hydroxide and kind of a smaller amount or limiting amount of HCl. And what that means when they react, because everything's a one-to-one relationship, when they do react, what's going to happen is all of the HCl is going to be used up first. And that's again because everything's a one-to-one relationship. So the smaller number will kind of be like the limiting reagent. The larger number will be the excess reagent, again, because everything's sort of a one-to-one relationship about it. So that's why we use the 4 here as our change part. Also, just logically speaking, if you chose the 6 as your change part, when you would get down to here, you would go for -6, which would get you not 0 down here, but it would get you -2 in that region. And obviously you can't have a negative concentration, can't have negative moles, in that sense. So logically speaking, you can't end up with a negative number there at the equilibrium per se. So you've got to go with the smaller number. Other questions on that? Okay, so like I was saying, there's really 4 distinct problems. It's really important to know sort of where you're at because it can extremely make the calculation easier, again, by knowing sort of what type of problem you should be doing. You can always predict the outcome. So again, when you start in this type of titration, all you got is a strong acid, which means you go right into the pH equation. Don't have to worry about anything else. Take the molarity, go into the pH equation. Once you start the titration to right before the equivalence point, you need to do 1 ice table in moles. The purpose of that ice table, which would represent the red part here, the purpose of that ice table is to figure out the new concentration of your strong acid. Once you get that, you convert it into molarity there after the first ice table and into the pH equation. At the equivalence point, which would be the dot or the green circle there around the dot, really is just that dot spot, really, is the point where our moles of acid equals our moles of base. And in this type of titration, you really don't have to do a calculation because no matter what combination you kind of put together, you'll always end up with a salt such as this one. And this salt will always be a neutral salt, which means the pH should always be 7 at the equivalence point. Now, once you get past the equivalence point, like we just finished up talking about, again, requires 1 ice table. Purpose of the ice table is to figure out the new concentration of your strong base that will be left over, because at that point, you're just dropping base in there. And once you get the concentration of the strong base after the first ice table, that will give you your OH minus concentration, and then that will get you your POH and then into your pH. Any questions on any of those? So why don't we try one here? We'll use some numbers. Let's do... So let's say we did the same reaction and we want to know what is the pH after 23 milliliters of 0.1 molar sodium hydroxide is added to 25 milliliters of 0.1 molar HCl. All right, so why don't you take a couple minutes or so and try to figure it out. It's the same setup as we've been talking about. Sodium hydroxide in the burette. We're adding the sodium hydroxide to the HCl. So take a few minutes and figure out what the pH is, and then we'll make sure everybody's got the right answer before we continue on our journey of titrations. Okay, so let's take a look, see how we're doing. So obviously we're doing a titration, so we are going to need to do an ice table. And that also means that we do need to get moles of everybody. So you may want to convert these guys into moles. So just to make sure, I hope everybody knows how to do this. So sodium hydroxide, again, that basically means 0.023 liters times our molarity, which is 0.1 moles per liter. And that's going to get you a lot of twos, I think. 0, 2, 3. That's going to get you 0.0023 moles of sodium hydroxide. We would also want to do the same thing for our HCl in this case. And again, 0.025 liters times our 0.1 moles per liter, going to get us 0.0025 moles of HCl. All right, so we're going to set up our ice table. We're going to go HCl plus some sodium hydroxide. Give us some sodium chloride and some water. We're going to put in our initial amount. So for our HCl, 0.0025. Again, this are moles. Our sodium hydroxide, 0.0023 moles, and 0. Now, again, sometimes people get a little lost along the way. So you can use your ice table. You could use the values that you see in there to help you figure out exactly where you are if you're not sure where you are at this moment. So we do know, again, we started with our HCl. We also know that we are adding our sodium hydroxide. And when we do a comparison of these two numbers, we see that the moles of what we are adding is less than the moles we started with. And again, using that idea that the equivalence point is equal moles, what we're adding is less. So what that tells us is we're actually before the equivalence point in this case. So again, we know we're before the equivalence point because if we were at the equivalence point, they would be equal. And since one is less than, and that's the one we're adding, is less than the equal amount, that means we're before the equivalence point. Again, the logic also tells us that the sodium hydroxide here is the smaller number, and that's going to be our change. So our change, again, you can't have that negative equilibrium number. So our negative change here is going to be the minus 0.0023 plus 0.0023 moles over here, going to get us at equilibrium. What we got there? Don't want to lose a 0. 0.0002 over here. We have 0 this guy and 0.0023 moles of this guy. Any questions on the ice table? Again, once we do this first ice table in moles, we want to convert it back to molarity. So at this point, the total volume is actually both of these numbers added together. So we started with 25 milliliters of the acid. We added 23 milliliters of the base to it. And that's like 48, which means we would want to divide each of these numbers 0.048 liters, which is our total volume at this point in the titration, to get our molarity. So if we do that, we get something like 0.00417. And over here, we get something like 0.0479. And again, if you're not sure what's going on, if we look at our ice table, we have HCl left over. We also have our sodium chloride left over. Again, this is a neutral salt. Also, we know that we are before the equivalence point, which means the only thing of concern at this point should be the strong acid at this point in this type of titration. So since this is a strong acid, that means that this is the H plus concentration, because HCl is a 1-to-1 relationship, right? When it breaks apart into H plus and Cl minus. And that means we can go right into our pH equation, which is minus the log of the H plus, and that's minus the log of 0.00417. Again, we're not worrying about that guy. Minus the log 0.00417 gets us something like a pH in this point of the titration of 2.38, which would be our pH value. Any questions on that? And we could kind of go back and see how we did. We're looking somewhere, what did I say, 23. So on this particular one here, 23 would be in this range. So at least it's higher than 2.2. It's less than 2.69. So pretty good that we probably hit the right number there. Any questions on those steps? So you need to know, obviously, what a strong acid, strong base titration curve looks like. You need to be able to calculate the pH anywhere along that curve that I choose. Or I guess if I'm really angry with you guys or not happy with you guys, everywhere along that curve, all 3,000 points. No, I'm just kidding. I could hear the dropping happening now. But you do need to be able to obviously calculate it anywhere along the way. So at the end of this titration here, again, really we had two things left over, which is sodium chloride. And again, that is a neutral salt, so you really don't have to worry about that in terms of pH. So the other thing we have is hydrochloric acid, which is a strong acid, and maybe I got it here. Hydrochloric acid, because it's a strong acid, it will break apart into basically a 1-to-1 relationship between HCl and H plus, which means whatever the concentration of H plus is, or the HCl, is the same as the H plus. So because it's all 1-to-1, that's how we knew the H plus concentration would be that. Other questions I could help you with? And speaking of sort of the equivalence point, by the way, at the equivalence point, there is a couple of ways you can kind of figure out the volume at the equivalence point. You could use M1V1 equals M2V2 if it's a 1-to-1 relationship. If it's not a 1-to-1 relationship, you cannot use M1V1 equals M2V2. You basically has to do like a little stoichiometry problem to figure out the volume to reach the equivalence point. So sometimes they may not tell you the actual volume to reach the equivalence point. They may just tell you, what is the pH at the equivalence point, and you may have to figure that out yourself. So again, if everything's sort of a 1-to-1 relationship, you could kind of use that M1V1 equals M2V2. If not, you have to do like a little stoichiometry problem. Or in reality, if it is a 1-to-1 relationship and the concentrations are the same, it takes the same volume to reach the equivalence point. So in our last example there, the sodium hydroxide is 0.1 molar, the HCl is 0.1 molar, and we started with 25 milliliters of the HCl, which means in this case, because everything is 1-to-1 relationship and they have the exact same molarity, it would take 25 milliliters to reach the equivalence point. So again, that's another way, if you sort of understand that when you only add 23 milliliters, you are definitely before the equivalence point, because it should take 25 milliliters to get there. Any questions on that? And again, if you do M1V1 equals M2V2, so you take 0.1 times 25 divided by 0.1, gets you 25 milliliters to get there. But again, you can only use that M1V1 equals M2V2 if it is a 1-to-1 relationship. Any questions on this type of titration? Okay, let's talk about another type of titration. And this type of titration is a weak acid and a strong base titration. And this setup is very similar to the last one we were talking about. So again, the setup here is our sodium hydroxides in our burette. In this case, we're dealing with acetic acid, which is a weak acid, and our weak acid is in our flask or our beaker. So again, in this titration, we're adding base to our acid. And we do see a similar sort of structure in terms of the curve. Again, we have our pH and our volume of sodium hydroxide added. We get this S curve that occurs. We also see a vertical, again, jump in the equivalence point towards the equivalence point, and also, again, a jump in pH to the equivalence point, a jump after the equivalence point in terms of pH. But this titration is a little bit different because what we're dealing with here is, again, a weak acid and a strong base. So let's talk about what happens at all the points here are the important segments of this curve. And we'll start just like we did on the last one, right here before we begin. So before we add any sodium hydroxide in this case, the only thing, so before we add acid, the only thing that we have, again, in that beaker, in this particular example, is our acetic acid. And we should know that our acetic acid is a weak acid, which means in order to find the pH, you pretty much need to do a Ka problem, which means you need to take the weak acid, you need to dissociate it into H plus and some acetate. You're going to do an ice table with molarity here. Again, you haven't added any volume, so you could use the molarity of the acid. These would be zeros. These would be X's like we've done before. And at equilibrium, molarity minus X, X, and X. This would go into your Ka expression. You would solve for X. And as you can see from our table here, X is equal to the H plus concentration. So once you solve for X, that will equal your H plus concentration. And then like normal, you could go into the pH equals minus the log of the H plus. Yeah, so the situation is just like the last one. So the base is in the burette, and you're adding the base to the acid, which is in the flask or the beaker. So in this case, we're adding the base, the sodium hydroxide, to the sodium to the acetic acid, but not at this point since we haven't officially started the titration. But in this titration, set up the same way: base in the burette, adding it to the acid in the flask. But this is obviously before we added anything. So this is like before you actually started the titration, you just put your acid in the beaker and before you actually start adding any base. But the next several ones will be when we add obviously the base. So you could also see here at the beginning, this type of titration is slightly different in terms of calculation you need to do, because in the first type of calculation or first type of titration, we were dealing with a strong acid, which meant you pretty much could go right into the pH equation. But here, because we're dealing with a weak acid, you have to go and do an ice table and really a Ka problem and solve for H plus. So again, slightly different here to begin with. We also see that, you might even start out with a slightly higher pH depending because of what's going on. So let's talk about what happens when we actually do start the titration. So let's go with, so as we start this titration, at the beginning of the titration, before the equivalence point here, so at the beginning of the titration, all the way up to before the equivalence point. So this is going to be before the equivalence point. So we'll take our reaction that's going to occur. So we're going to have our acetic acid that's going to react with our sodium hydroxide. And we're going to get some sodium acetate. And we got there sodium acetate and some water. So we are going to do an ice table here. And just like before, we do need to do it in moles because, again, we're adding volume, so we want to do it in moles. So we liked that number before, so I'm going to start with the same number as what we did last time. So I'm going to make up that number that we're starting with 4 moles of acetic acid in this beaker. And again, we're going to add now our sodium hydroxide to it. Because we are, again, before the equivalence point, much like we talked about before, since the sodium hydroxide is what you are adding, that means that the moles of what you're adding should be less than what you started with, because, again, you're before the equivalence point. So I'm going to use the exact same numbers I did before, which is 2 moles, and this would be 0. The change part here is going to happen just like it did in our first titration curve. Because the sodium hydroxide is the limiting amount of moles, it's going to get used up, which means the change in this case is going to be -2, -2 plus 2. Obviously, water is not going to affect anything, which is why I'm ignoring it. At equilibrium, we will get 2 moles of this guy. We will also have 0 of that guy and 2 moles of this guy. So this ice table is very similar to sort of the approach that you did in the exact same location on the previous titration curve. And just like pretty much good practice to do at this point, once you've done that first ice table, you should convert it back to molarity. So we're going to take these moles, we're going to divide it by the total volume, which, just like we did before, would be obviously the volume of acid we started with and the volume of base that we added into it. And again, at this point, if you're not sure what to do or what's happening, you can use your ice table to help you out. So if you look at your ice table, you will see that you have this guy left over, which is acetic acid. You also have this one over here, which is sodium acetate. So now you have acetic acid and sodium acetate left over. And this should also ring a bell to you that acetic acid and sodium acetate are related to each other. That is a weak acid and its conjugate base. That is also known as a buffer. So at this point in the titration, you are actually left over with a buffer. So what that means is if you want the pH of this solution at this point, because it is a buffer, you actually have 2 options. You could do the ice table, because if you like ice tables, you could do an ice table, which the ice table would look just like the above table, except that you would have a number on both sides. So you would have a number here, and you would have all the X's and all that. But the only difference would be is it will look just like this table up here, but you would have an initial number here, which would be this number for acetate. Or again, the easier move at this point is, because it's a buffer, to go right into your Henderson-Hasselbalch equation, the pKa plus the log of the base over the acid. So you could see that as we start the titration in this type of titration to before the equivalence point, it is very, very different than what we did on the last titration. You need at least 1 ice table, and that ice table is basically to figure out what the concentration of your buffer will be. And then you do have options. You could either do a second ice table, where the initial concentrations are from the equilibrium concentrations of the first, or probably the easier move is go right into the Henderson-Hasselbalch equation. So in this type of titration, anywhere from when you start to before the equivalence point, you will always end up with a buffer at this point, which is why it's sort of gradually making its way up in terms of the pH in that point, because you do have some buffering that's occurring. Any questions on that? This is also just a sort of side note, if you will, and sort of the idea behind Lab 7, or part of Lab 7, is this is exactly how you could make a buffer from the combination of a weak acid and strong base. And that's what we did here, right? We took a weak acid and we combined it with a strong base. And what we were left with once that was done reacting was a buffer. And you can see this is what I was talking about before, that you can make a buffer from a weak acid and a strong base, or a weak base and a strong acid as well. Same idea happens. But you can make a buffer from that reaction. But the buffer doesn't happen until, in this case, for example, all of the sodium hydroxide gets used up. So just so we're clear, the buffer is not the acetic acid and sodium hydroxide. The buffer comes from the end result of that reaction, which is the acetic acid and the sodium acetate that's left over. And as you can see, at equilibrium, there's no more of the sodium hydroxide there. So that's what I was talking about the other day, where I said you can make a buffer from a reaction of a strong acid with a weak base, or a strong base with a weak acid. But it doesn't become a buffer until all the strong acid or strong base gets used up. The result of that reaction is how you get a buffer. So this is a prime example of how to sort of make a buffer, as opposed to a traditional way of making a buffer where you just take both parts and you mix them together. Here you take one part of the buffer and you make the other part through a chemical reaction. Any questions on that? All right, so this one's slightly different, as you can see, as we're progressing through here. So let's talk about what happens when we do reach the equivalence point in this titration. So at the equivalence point, which again is our point where our moles will equal each other, and represented here by our dot, and I'll just circle our dot. We'll represent it with green. So let's talk about what happens when we get there. So if we are at the equivalence point, again, what that's going to mean is the moles of acid should equal the moles of base. So if we take our reaction, and again, we do want to do this in moles because we're adding. So we'll go with our 4 moles of this guy to start with. So again, this is what we're starting with. This is what we're adding. And again, because we know we're at the equivalence point, the moles of sodium hydroxide that we add should equal the moles we started with. So that means that we should have equal numbers of moles here because we are at the equivalence point. We'll do 0 here. Again, the change part, you can't really mess up. That's going to be -4. That's going to be -4. And that's going to be +4 moles on all those. Which means at equilibrium, none of the acetic acids left, none of the sodium hydroxides left. We have 4 moles of this guy, which again, we are going to convert back to molarity. Again, water, no effect, so we're not going to play with any numbers. So at this point, a little bit different, we do see that what we are left with at this point in the titration is sodium acetate. And this is a salt. And that salt, as we talked about when we talked about salts, will break apart into a sodium ion and an acetate ion. And the important part about a salt, if you remember, is will it react? And will it react with water, right? So at this point, what we need to figure out is any part of that salt going to react with water and go through hydrolysis? And we know that sodium won't because it's group 1. But our acetate here obviously came from acetic acid, which is a weak acid, which means this is going to be relatively strong, right? And this is going to act as a conjugate base. So in this point in the titration, you will make a salt just like we did in the first one. But the difference is that salt will go through hydrolysis. So it's going to require a second ice table, which will be the acetate plus the water, just like we talked about with hydrolysis reactions. Because this is going to act as a base, it's going to accept the H+. And we know it's going to react as a base because it came from acetic acid. So, right, so it came from an acid. It's going to act as a base, which means it's going to accept the H+. When it does, just like we talked about with our hydrolysis reactions, we will make where it came from, and we will make some hydroxide. And just like we talked about with our salts and our hydrolysis reactions, right off the bat, we see hydroxide. We should know that this solution should be basic. We also know we should be using a KB value as well. So your ice table, I'll just say, I'll circle this one here. We're going to take the molarity from our first ice table, and this will be our initial molarity here. So I'll just circle it. These guys will be zeros. We'll do a minus X plus X plus X. And again, at equilibrium, our initial molarity minus X, X, and X. And as we talked about last time, at this point in the titration, you probably will just have the Ka value, just like before. So you need to make sure you get the Kb value, right? So using the Kb, you could solve for X. X in this case, though, equals the hydroxide concentration, as you can see from that table, which means you could get the POH and then to the pH. So definitely much different than the first titration curve where you pretty much just lay up 7 and you're good to go. Here, you need to do 2 ice tables. First ice table is basically to figure out the concentration of your salt, and that salt will always go through hydrolysis in this type of titration. That hydrolysis will always produce hydroxide, and that means that you also always need the Kb value. You then need to do a second ice table in molarity where you figure out X. X will be the OH minus concentration and will allow you to get to the POH and then to the pH. Any questions on that part? So obviously very different. And we can see that here, unlike the last one where it was 7 at the equivalence point in this titration, 8.72, which is obviously basic. So to finish up this titration curve here, if we continue past the equivalence point, so if we go past the equivalence point here, all the way to the end, at this point, we are continuously dumping the sodium hydroxide in. So let's see what happens at that point. So we go past the equivalence point. We'll have our reaction. And initially, again, if we started with our 4 moles, because we are past the equivalence point, we should know that the moles of sodium hydroxide now will be more. So we'll use 6, 0. We also, just like we saw before, we'll have a change that occurs between these two things. And the acetic acid in this case is the limiting, which means the change would be -4, -4, +4, which means at equilibrium 0, 2 moles, and 4 moles of this guy. Just like before, we're going to convert these guys into molarity by using the total volume. And at this point, we do have sodium hydroxide. We do have sodium acetate. Again, you should not use the Henderson-Hasselbalch equation because these two things are not a buffer. So you don't want to do that because you got 2 numbers. But let's take a look at these things. So we did see that in the last part of the problem that the sodium acetate would go through hydrolysis. So it obviously would affect the pH. It's going to act right as that conjugate base, right? We also have sodium hydroxide here, which is a strong base, which should also affect the pH. So between the two, at this point in the titration, the stronger base is sodium hydroxide. So typically at this point in the titration, we ignore the contribution of the sodium acetate because remember, the sodium acetate essentially needs to go in, find some water, do a little reaction to produce hydroxide. While the sodium hydroxide pretty much just needs to go for a swim As soon as it goes for a swim, it's going to produce a lot of OH minus. So at this point in the titration, once you pass the equivalence point, you pretty much will just look at the contribution of the strong base, which means that that is going to give you your OH minus concentration, which means, again, you could get to your POH and again to your pH at that point by subtracting 14. So past the equivalence point in this type of titration, you need to do one ice table. The real purpose of the ice table is to figure out the concentration of the strong basis left over, and then you could go to your OH minus and then to your POH, to your pH. So this titration curve, which looks remarkably similar to the first one, a little bit different in terms of sort of its scope and verticalness, if you will, but is 4 distinct problems. The good news is you should know how to do all 4 of these problems. The bad news is where most people get into trouble is they're not sure what they're doing. So that's why it's important to know sort of where you are in the titration curve, because even before you start the calculation, you should have a really good idea as to what type of problem you should be doing. Should you be doing a buffer problem? Should you be doing a hydrolysis problem? Should you just be figuring out the POH? You know, should you be doing a Ka problem? So extremely important titration problems, to know what type of titration you are doing, where you're at in the titration curve, because again, if you start out before you actually jump into it, which is what a lot of people do, they just jump right in and go, I'll just kind of figure it out as I'm doing it, rather than going, oh, I'm right here in the titration curve, and then this part I should end up in a buffer. So I know I should be heading down sort of the buffer path as I'm doing my calculations. So super important to sort of understand what's going on, where you're at, so that you can have a good game plan as you head into the calculations. And that's where a lot of people just sort of get into trouble, because they don't really have a game plan. They're not really sure what's going on. All they know is a lot of times is, oh, cool, at the end of my ice table, I got 2 numbers. What equation uses 2 numbers? I know, Henderson Hasselbalch. I'll just keep using that all day, every day, you know, twice on the weekend, all that kind of stuff, right? So it's super important to sort of know what's going on, where you're at. It makes these calculations that much easier. Any questions on that? Okay, so it's a good place to sort of stop here for today. So let's talk a little bit about lab, what's sort of going on. So we kind of skipped over experiment 6, which is buffers. Today is experiment 7, which is also buffers. So I think what we're going to tentatively do right now for this week in terms of the labs is I think we're just going to move everybody down a day. So we're going to start with experiment 6 today. We'll see how that goes. And then we'll probably do experiment 7 tomorrow, 8 on Wednesday, and then maybe 9 on Thursday. So we'll kind of see how it goes, but that's a tentative plan. So we're going to tackle most likely experiment 6 today, which was again the one that was scheduled on Wednesday. And because I think on Thursday of this week, there technically is not a lab scheduled. We're supposed to do some lecturing, but I think we're kind of okay in terms of pace of lecturing. We kind of did our extra lecturing last week. So I think this week that's sort of probably the plan as of now. I'll let you know if anything changes, but as of now, I think we're going to focus in probably on experiment 6 today, and then we'll probably do experiment 7 tomorrow. Maybe we'll look at some of experiment 8. I'll decide, but that's sort of the ideal plan. Is we'll probably just kind of go one at a time. Yeah, I'll go back to that for you. Any other questions on that there? Okay, so we ran a little bit late here, so let's take a little break so we could stretch. Why don't we shoot for 3:10? We'll start lab. And again, we're going to be doing, I think for the most part, we'll probably just do experiment 6 today, I think. I think that will be what we'll focus on. All right, if you're good, I'll see you about 3:10. And again, make sure you hit here in the chat if you didn't do so, and we'll continue on, all that good stuff. Cool. You're all good with the slide? Perfect.